Hello, you're listening to Avril Sorter talking about CCNA wireless. In this lesson, we're going to talk about how a wireless LAN actually operates, and it's really important when you're looking at how to deploy a wireless LAN that you understand fundamentally how you actually connect and send data backwards and forwards. So the first thing we want to talk about is the Service Set Identifier, the SSID, and this is the name given to the wireless LAN to identify it. So for instance, in my home, I simply call it Avril's network. Now on an access point, it's possible to have multiple SSIDs. And so in my home, I have Avril's network, and I also have guest wireless LAN. And so when people come, I can put them on the guest wireless LAN and have different passwords, etc. Now, there's nothing regulated, and there would be nothing to stop me calling my wireless LAN AT&T's network. Now, in a little while, we're going to talk about the beacon, and the beacon is typically transmitted from the access point, and included in that beacon is the SSID, and most people will incorporate the SSID into that beacon and it is broadcasted, but it is possible to stop it being broadcasted, in which case you need to know what the SSID is in order to be able to connect to that network. Now, it's not exactly secure. By hiding the SSID doesn't make your network more secure, because it's possible to sniff over the air and determine that SSID, but it does prevent the casual person finding it. Now, when you connect to an access point, an enterprise access point, you can set up multiple SSIDs. And so I might set one up for engineering, one up for marketing, one for finance. And what those different SSIDs can do is they'll map to different VLANs. And so in this way, I can protect access to different parts of the network, because I can map that VLAN then to connect them to say, okay, you can get to this resource, but you can't get to this resource. Now, one of the things that you must remember when you're deploying your wireless LAN is that if you want your users to roam, between access points, between buildings, etc., then it's very important that you make sure the SSIDs match. Like, you can't move from a network called Avril's network and then go roaming off to Sorter's network. You want to make sure everything's called Avril's network, and then you can set up the roaming to go between them. Now, you have to do a lot more than give it the same SSID to make roaming work, but if you don't make the settings the same, roaming will not work. Now, I'd mentioned the beacon earlier. Now, the beacon may or may not be sent from the access point, and Cisco actually recommend that you do leave the beacon turned on. For some people, for security reasons, will turn off the beacon, but it does not really protect your network against people that can sniff the network and hack into it, because the information sent out on the beacon is also sent out on what we call probe responses, which we'll talk about in a moment. So typically you would send out the beacon, and typically is sent out about every 100 milliseconds. And the beacon contains information about the access point and therefore how to connect to it. And so one of the most important things on the beacon is a timestamp, and the timestamp is added at the moment that the beacon's actually transmitted. And so I'll use that timestamp to sync the clock on my client with the access point, so it puts us into synchronization mode, so that my clocks are synchronized with the beacon. It'll tell me what the beacon interval is. And like I said, the beacon interval is normally about every 100 milliseconds. And if I can't hear the beacon after 100 milliseconds, and let's say I've been waiting and it's now been 200 milliseconds and I still haven't heard a beacon, then that would indicate that I'm out of coverage and I should look for another access point. It'll tell me the capability of the access point. So for instance, it'll tell me if it's supporting features like quality of service, the different security mechanisms, etc. We talked about the SSID. The SSID may or may not be included in the beacon. Typically it is included in the beacon. It also tells me what rates are supported. What I'm talking about here is the data rates. Now let's say this access point had been set up to support voice calls and had a minimum supported data rate of 24 megabits per second. So even though I could connect further away from the access point where the data rates may have dropped to 12 or 6 megabits per second, I know that it won't support me at those data rates, that the minimum data rate has been set to 24 megabits per second. So I find that out when I listen to the beacon. Based on this information and the signal strength, I can then decide, do I want to connect to this access point or do I want to connect to another access point? So when I first turn on my 802.11 device, so this would be when I open up my laptop and I turn on the radio, open up my tablet, open up my smartphone, what's going to happen is that I will start looking for wireless networks. And what you've seen before is that I might have a radio that operates in the 2.4 gigahertz band and also in the 5 gigahertz band. And what I'm going to do is I'm going to scan the different frequency channels in the 2.4 and the 5 gigahertz if I'm capable of supporting both radios. And so I'll scan them and then I will select one of those access points to connect to. And my decision on how to connect may be based on the SSID, on the signal strength. There could be a variety of factors. As a user, I get to select, oh, I want to connect to the Cisco network. Oh, I want to connect to Avril's network. But if there's multiple access points and different channels, then typically you'll connect to the one that you hear the best. And the algorithms that determine which one you connect to are proprietary to the vendor that created the radio product in your device. Now there are two forms of scanning. There is active scanning and passive scanning. So let's take a look at active scanning first. In active scanning, this is when I actually send a probe request. Imagine, if you would, that I am just turned my radio on. So what I do then is I tune it to channel 1 on the 2.4 gigahertz band and I send a probe request frame. I may or may not get one or more probe response frames back. I then go to channel 2 and repeat the process, send a probe request, I may get a response back. Go to channel 3, repeat the process, go to channel 4, etc. When I've finished scanning all of the frequencies, I then look at all my probe response frames and say, okay, this is the one with the SSID that I want to connect to, and it has the strongest signal strength, and then I'll go ahead and connect to that access point. Now the probe response frames contains all the information that was contained in the beacon. And that's why I said to you earlier, if you turn off the beacon, it doesn't really make any difference, because all I have to do is listen to the probe response frames, and then I have all the information that was contained in the beacon. The advantage of doing a probe request as opposed to listening to the beacon is simply the fact that I'm not waiting to listen for the beacon. So I can go to channel 1 immediately and then send my probe request and get a response back. Then go to channel 2. Then go to channel 3. So it's much quicker if I'm in active scanning. The disadvantage, of course, is I'm actually sending probe requests, which take up valuable RF resources. And so in an environment which isn't heavily loaded, you can set your clients to do probe requests. In an environment which is heavily loaded, then you may want to turn active scanning off in your environment. And then you can have passive scanning. And this is what we were talking about earlier, is that I will tune to channel 1, I'll listen for the beacons. Now I obviously want to listen for a period that's longer than the beacon interval, and I don't really know what the beacon interval is on different access points. So maybe I'll listen for 200 milliseconds, then I'll tune my radio to channel 2 and I'll listen for 200 milliseconds, tune it to channel 3, listen for 200 milliseconds, etc. And again, once I've collected all the beacons, I can then make a decision as to which SSID I want to connect to and then which access point based on the signal strength. Most enterprise organizations will define a policy for how clients can connect to the wireless network, and whether you allow active or passive scanning can be part of setting up that policy of how users can connect to the network. And once I've discovered which access point I want to connect to, now I need to begin a communications with that access point. And the 802.11 standard defines that you should send in an authentication frame. And you can do open system authentication. Let's say this access point is open, it has no authentication mechanisms on it. Then I would send in an open system authentication request, in which case I would get an authentication frame response, which if the access point's not too heavily loaded, it will say, yes, you have authenticated with this access point. You can do a shared key authentication. And in this case, I send my authentication frame in, and the access point will send me back a challenge text. I will respond back to that challenge text using my shared secret key. The access point will say, oh, this person obviously has the shared secret key, and therefore they have successfully authenticated, and then I'll get an authentication frame response message back accepting me as authenticated on that access point. You could also do 802.1x authentication, and this is typically what you see being done in a business. And there's really two ways of doing this. You can do it at this point in time. You can send in an authentication frame, and that will trigger an 802.1x exchange with an authentication server. Or what you can do is you can do open system authentication at this stage and trigger in 802.1x after you've associated and after you've got an IP address. Once you've done the 802.11 authentication, you need to go on and associate. Now, association is forming a logical connection between the client and the access point. When I send in an association request frame, I'm also telling the access point about myself. I would tell it, for instance, what data rates I can support. Do I support quality of service? If I'm 802.11n, how many MIMO antennas do I support? The access point will then come back with an association response frame. And the association response frame includes what's called an association ID. And so from this point on, the client station has a unique association ID and is going to use that association ID in various exchanges going forward between the client station and the access point. Now, the way to think about it is that I have several clients that want to gain access to the RF medium, and in 802.11 I can only have one client transmitting at one point in time. If I have two clients transmitting at the same time to the same access point, there could be a collision and there's a risk that neither of them will get heard. And so somehow I have to find a way to share the RF medium. And there's actually a few different methods defined in the standards to allow me to do that. Now, the first method is called Distributed Coordination Function, DCF. It uses a collision avoidance scheme. So it's a CSMA-CA, collision avoidance, in comparison with Ethernet, which uses a collision detection mechanism. Now, the DCF mode of operation is the one that's most commonly deployed. It was in the original specs, and up until a few years ago, it was the only one I ever saw being deployed out there. The original specifications also included another method called Point Coordination Function, PCF. This was also part of the original specification but was never really implemented. And what it does is it polls you periodically. So during the period where you're operating in a PCF mode, all the stations are quiet and the access point will poll the client and say, client number 1, do you have anything to send? They didn't say anything, so I'm assuming they don't have anything. Then I'll poll station 2. They sent some data back, so I know they have data. Then I poll station 3. And they're only allowed to transmit when they are polled by the access point. Now, these two modes of operation is not one or the other. They can both coexist, and I can be in a contention mode where I use DCF, or I can be in a contention-free mode when I use PCF. Now, the problem with PCF is that you literally have to define and say, oh, I'm now going into a contention-free period, and then I can poll all of my different stations. The problem is that when you go into a contention-free period, it can vary in time. And I cannot guarantee that every 100 milliseconds I'm going to go in to a contention-free period, for example. And so what happens is if I have a device I need to poll, let's say every 20 milliseconds, I can't actually do that in PCF because I can't control the delays. And so one of the enhancements that was made a few years back was to extend the capabilities and include something called the hybrid coordination function. And this is based on the point coordination function, i.e. it does polling, but it now deals with the timing problems that I had. And now I can poll a station both during the contention period and the contention-free period. So if I need to poll you, I don't have to wait for the contention-free period to be announced. And so I've dealt with those timing issues. Now, is talked about, and you'll see a limited implementation of it. Largely what you still see is DCF. So seeing that DCF is the most common thing you're going to see out there, let's spend some time talking about the process in more detail. And this is an example of Ethernet when you've deployed two stations on the same wire. And so this is like your old legacy kind of Ethernet connections, but just to show you what happens so we can talk about why DCF is different. So in this example, I've got two stations and they happen to transmit at the same time. So they both listen to the wire and they go, oh, I can't hear anything. The wire is clean, i.e. there's no voltage shift going on it. Let me go ahead and transmit. And in this example, two stations happen to transmit at the same time, and so there happens to be a collision. Now, when two signals go down a wire, they will combine, and therefore you'll see a voltage shift. And therefore, because of the wire, both stations will hear that there's been a collision. And what they'll do is they'll say, my goodness, there's been a collision. I will back off for a random period of time, and I'll try again. And if both stations select the same random period, then they're going to transmit at the same time, in which case they detect another collision. They will then double their contention window, recalculate a back-off period, and try again. And eventually, one of them will have a smaller back-off period and be able to transmit. The problem in a wired network is that I can't detect a collision. And the way to think about this is, imagine if you were on one side of the football track and you were shouting, and I was on the other end of the track or the field, and I was to whisper. You wouldn't be able to hear me, i.e. I cannot detect incoming signals while I'm shouting. So if you have two stations transmitting at the same time, those stations will not be able to hear any other transmissions. So you cannot do collision detection like you can in a wired Ethernet network. Instead, you have to use collision avoidance techniques. And the way we do collision avoidance techniques is two things. We do a physical channel assessment and what's called the network allocation vector, which is like a logical channel assessment. So a physical channel assessment is literally when I listen. Can I hear anybody transmit? If I can hear noise in the band, then I won't transmit. And that noise may be caused by another station in the same wireless LAN as me. It could be created by a Bluetooth device, the microwave oven, a neighboring wireless LAN that's on the same channel. If the channel's quiet, I still don't transmit because I still got to look at the network allocation vector. And the network allocation vector is a logical way of seeing if the network is busy. And I'll show you how that works in the next couple of slides. So to understand the NAV, the network allocation vector, I want to show you how I send data. And the way 802.11 was originally written, this is not including the quality of service enhancements that were defined later, is that a station will listen, and if the physical medium is free and the nav is 0, then it will go ahead, after waiting a small back-off period, it'll go ahead and send a data frame. If that data frame is successfully received from the access point will respond with an acknowledgement. Included in the data frame in the MAC header is a duration value, and the duration value is the nav. I am literally telling everybody, hey, I'm going to be transmitting for this period of time, and is calculating how long it's going to take to send that data frame for the access point to respond back and send an acknowledgement back. And so anybody hearing that data frame, let's say station 2 in this example is close enough to hear it, will hear that duration value and will set its nav. So it's now set its logical clock to say I cannot transmit during this period. When the access point responds with an acknowledgement, it will set the nav back to 0. Anybody connected to the access point hearing that acknowledgement will then set their nav back to 0, and in which case they will then say, okay, is the physical medium free? Oh my goodness, it is. Is my nav 0? Oh yes it is. So therefore I wait a random back-off period, and if during that time the medium is still free, I can go ahead and send some data. So what you're seeing here is when a station does transmit, it includes the nav value to tell any stations close to it, please be quiet during this time because I'm sending data and I'm waiting for an acknowledgement. So it can be quite difficult to follow it in words, and so this flowchart will help you understand what happens. So here I am, I'm starting, and I want to send a data frame. I listen. Did I previously set my nav? If I do, then I go back here and I wait until that nav expires down to 0. If it's expired down to 0, or it is already 0, then what I'll do is I'll go on and physically sense the medium. And so I'm listening. Do I hear any noise, any signals in the band? As long as the noise is below a threshold, I will assume, oh, it's okay for me to transmit. If there's noise there, then I will assume that the medium is busy and I cannot transmit. I will come here, wait a random period of time, and try again. If the medium is idle for a random period of time, then I will go ahead and transmit my data frame. If I don't get an acknowledgement back, I will assume a collision, and then I will recalculate my random backoff period, and then I will try again. And I keep following this process until I'm finally able to transmit. And each time I come down here and I have a collision, I double my contention window from how I calculate the random backoff period. And in this way, as my random backoff period is selected from a larger and larger number, I'm avoiding collisions with other wireless LAN devices that are operating, and eventually I'll get an acknowledgement back. Now, the heavier the wireless LAN is loaded, then the more collisions I'm going to get, and therefore the performance of the wireless LAN will go down. So most access points will limit the number of clients that are allowed to connect, simply because if it allows too many clients to connect and your collision rate goes up, your performance will go down considerably. So here is an illustration, and in this illustration I have an access point and I have two stations. Station 1 wants to transmit. At point 0 it says, oh, my nav is 0 and the medium is free. So I then wait what's referred to as a diff, a DCF interframe spacing interval, plus my backoff period, calculated using a random number selection. If the medium is free all during this time, I will go ahead and send my MAC frame. In the MAC header, I will include the duration value, which includes the time it will take me to send my frame, plus what's referred to as the CIF, plus the time the acknowledgement takes to come back. Station 2 can hear Station 1. When it hears this data frame, it will set its nav. And Station 2 will not transmit during this time whether or not the medium is free, because it knows that it's been reserved using the nav. Now the CIF is the short interframe spacing interval, and this is defined in the standards as the time it takes for the receiving station to process the incoming frame and to send a response. So the acknowledgement must be sent within a CIF. And remember, when the acknowledgement comes back for this data frame, the duration value in the acknowledgement is 0, and anybody hearing that acknowledgement will then set their nav back to 0, in which case they can start their transmission period of listening is the medium free, waiting a diff plus a random backoff period, and then trying to transmit. Now the 802.11 standards initially defined 3 frame types. They are called data, control, and management. And every MAC frame that's sent between an 802.11 client and an 802.11 access point will be one of these frame types. Now, at the beginning of this lesson, we talked about authentication and association and beacons. and those are management frames, and we use those to actually create and maintain a connection between the station, the client, and the access point. There are also control frames. When you're sending data, sometimes before sending the data you'll do a request to send, and you'll request the access point, can I send some data, and the access point will respond back with a clear to send. We also saw acknowledgement. Those are control frames. Those are used to help manage and assist in the exchange of data. Can I send some data? Yes, you can send some data here. I'm acknowledging that that data was received successfully. So those are control frames. And of course, data frames is the frame that's actually containing your user data. In 802.11, the initial standards define sending one frame at a time. So you send one frame, get an acknowledgement, send another frame, get an acknowledgement, send another frame, get an acknowledgement. And we would take turns. Whoever calculated the shorter backoff period would transmit first. And then they'd send one frame, and then again whoever calculated the shorter backoff period would then send their frame. And so we share the RF medium using these backoff periods, and whoever calculated the shorter backoff period can then go ahead and transmit a frame. But it's not possible to hog the whole medium to send a big video stream, because we're giving you access to it one frame at a time. Now, as quality of service was added to the specifications, it's now introduced a transmission opportunity, and you can now send multiple frames within a transmission opportunity. So I can say, okay, you've got the medium for 10 milliseconds, transmit what you want during that time. But that was an enhancement with 802.11e quality of service. So for this demonstration, I thought it would be really fun to take a look at what 802.11 MAC frames actually look like. So we're going to take a look at the beacon frame, and we're going to take a look at the content within the beacon frame. So in this demonstration, I wanted to show you what the 802.11 packets look like, and to do that I'm going to bring up Wireshark, and many of you might be familiar with Wireshark because it's a great tool for sniffing the wired environment. However, what I'm going to do is I'm going to use it with my ear PCAP adapter, which is a wireless adapter, and therefore will capture packets both in the 2.4 and the 5 gigahertz band. We could look at our interfaces here, and you can see here that I'm starting to capture packets with my ear PCAP adapter. There we go. So we can see that I'm busily there capturing 802.11 traffic here. So let me just move this up. There we go. And let me see if we can find a beacon. Here is a beacon frame. We can see here the time it was captured. Let me just move this out of the way. The time. We've got the source and destination MAC addresses. Here, of course, is a broadcast MAC address. And over here you can see is a beacon frame. I just scroll this across. You can see here the beacon interval, and here's the SSID. So let's go take a closer look at that down here. So here's the frame control field. I click on that. You see that? You can see here is the type of frame, and it's a management frame. And this subtype here would indicate that it's the beacon. You can see the duration value is set to 0 because of course this is just one frame, and I'm not looking to reserve the resources to get an acknowledgement back. We come down a little bit more. You can see is a broadcast MAC address. Here's the MAC address of the access point, which is the source address. It's not been fragmented, and here's the sequence number, and here's the frame check sequence. Open this up. Let's take a look at the parameters as being held within the beacon frame. You can see here is the timestamp. So this indicates the time when the beacon was actually transmitted. The timestamp's actually added at the point of transmission, not when the MAC frame's created. It's actually put on there when it's transmitted. Here you can see the beacon interval, as I said, is normally set to 100 milliseconds, so you can see that here. And let's take a look at the capability information. So it's operating in an infrastructure basic service set. I'm using a short preamble on the physical layer. I've got power saved delivery mode here. It says it's not implemented on this one. I've got 802.11b here, and IRFDM modulation not allowed. So it's just using IRFDM. I've got 802.11b turned off on this access point. Let's take a look at our tag parameters. So here you can see here it's set to Avril's network. Here's my tag length here, my SSID. Here are the rates that I support. Here you can see I'm operating on channel 11. If we come down a bit more, we can see my extended rates going up to 54 megabits per second. My extended data rates. Here's my security information, the robust security network. We can see here, this 48 here applies to the initialization vector. Here you can see I'm using TKIP, a pairwise cipher suite. Take a look at this last one. And again, you can see some of the parameters here that I'm setting for security. I take a look, see if we've got any vendor-specific information. See here, Microsoft, WPA information element. So Microsoft's included some specific elements here that they're using to provide some additional features and capabilities. So that was our beacon frame, and so you can see that I can listen to that, I can get the SSID, etc. Let's take a look at some of the other frames that we're also seeing here. So here you can see a reassociation request. Here's an acknowledgement. Here's a clear to send a clear to send, and then I'd expect to see a request to send above that. Here you can see contention-free end, contention-free acknowledgement. Here's some data frames. Here's an authentication frame. So again, many of the management, the control, and the data frames that we were talking about in the previous lesson are shown here on this demo. Here's another acknowledgement. And let me show you, I'm still collecting data here, and just so you can watch it coming in live. You can see there the probe responses, probe requests being made, and so you can see the kind of traffic that's being generated. And here we're looking at 2 access points. I'm not doing very much on them, so I'm not sending a lot of data, and you can see I'm regularly sending out probe requests. I've got beacons going on as my devices continue to connect and send some data. So I hope you found this interesting. If you've not done this before, do think about getting a wireless capture card and putting it on Wireshark because I think you'll find this particularly valuable just to take a look at these packets. And again, it's very easy to do. You can just literally take any of these packets at all and then just open it up and take a look about what it's got in it. So like a request to send, a beacon, etc. You can literally look at the type of information. I mean, look at this request to send here and the duration, and this is in, so I'm looking for it here, and so I can really start to understand what is the data that I'm actually transmitting over the air. So again, I encourage you to do this, and most of you are probably very familiar with Wireshark as a tool for sniffing over the wired networks, and here I'm using it to sniff over the wireless networks. So I hope you found this demo interesting. Thank you for listening.